Hi folks, welcome back to another Lab in Theory video. In this tutorial, we'll be looking at how we can solve reaction kinetics using MATLAB. This is great if you're a student starting out in a reaction engineering class, or if you're a practicing chemical engineer and you want to brush up a little bit on how you can solve some ODEs. Now, in this tutorial, what we'll be looking at is the iodine clock reaction, or the Landau reaction. This is a very striking, popular reaction, which I will link up in the video. You can click on it. I have a recording of myself performing this reaction way back in the day. It's very fascinating. You start off with two solutions, you mix them together, they're clear. Then, at some point in time, later on, all of a sudden it changes color and it turns this deep violet blue color. It's a very striking reaction. It's very cool. It's featured in many high school chemistry labs, and so what we want to do today is to use that reaction and to develop a kinetic model, or to implement a kinetic model to be able to translate a reaction mechanism from paper to MATLAB and solve it appropriately. I have a paper here open which provides a mechanism for the Landau reaction. Let's go ahead and scroll down on this paper. I want to emphasize that this is not the kinetic mechanism for this reaction, but it's a proposed mechanism. It doesn't really matter. I wouldn't sweat the details. The main purpose of this video is to be able to take a series of equations, a series of reactions, and translate them into a set of ordinary differential equations and solve them in MATLAB. Now, I mentioned that in the video, that I did link a video of this reaction, which you can watch. The ingredients that go into this reaction, of course, are iodate, which are IO3-, and then sodium metabisulfite, or sodium bisulfite, which is NaHSO3, sulfuric acid, H2SO4. It's the catalyst. And finally, a starch indicator, which, when elemental iodine is formed, it will bind with that iodine and form that deep blue-purple complex, which is so striking in this reaction. Now, in this paper, two mechanisms are given. The first mechanism, scheme 1 here, is a series of A through G reactions, which document the iodate sulfite ferrocyanide system, and then they provide a mechanism for it. So this is the overall process. The mechanism, these are the elemental reactions that take place, that they postulate for this reaction, and these are what we are going to be modeling. Conveniently for us, they of course give us some nice rate constants here, which we can translate into actual code. A few points I wanted to highlight here, literally of course, I went through. I highlighted a few extra things, which are the concentrations, things we'll run at. They're provided here as well. We'll come back to those in a little bit. I just wanted to point that out. The pKa of HSO3-, the bisulfite here, we'll be using that in a little bit too. Now, with that being said, let's get started. This is the mechanism we're interested in. I want to point one thing out, though. We're going to ignore... we're going to ignore the reactions 10 to 13 here. Those 1, 2, 3, 4 reactions. I can't do basic math, apparently. The reason is because they just add additional complexity, and we're not really interested in the ferrocyanide reaction. We're mostly interested in the iodine clock reaction part of this mechanism. So, the first thing we'll do is we'll create a new file here in MATLAB. We'll give it a name, like, say, let's see, Landau run file. And I'm going to open this up in my editor right here. So Landau, again, is the name of the reaction. I'm just going to call it the Landau run file. This will be the run file for the reaction. I'll create another file, and I will call this the Landau mechanism. Okay, so this will hold the kinetic mechanism, which we're going to code up from here, and Landau run file will contain the commands necessary to run the ODE model that we have here. Now, of course, in this tutorial, I assume you have a basic understanding of reaction kinetics, a basic understanding of ODEs as well, and also a basic knowledge of how to navigate MATLAB. If you're not familiar with that, check out my Intro to MATLAB video, which I will link right in this video right now. And if you are interested in knowing more about ODEs, let me know in the comments box below, and I'll be sure to make you a video dedicated to discussing ODEs. Okay, now, enough talking here. Let's get started and define our reaction mechanism. So in this file, what we'll do is we will define a function, and what we want to return are derivatives of the concentration, so dc. Again, when you have a reaction rate, you want this is not part of the code, but you want to model the change in concentration as a function of time. That's what we're modeling here. And of course, we want to integrate the different concentration derivatives to get the concentration profiles themselves as a function of time. So that will be equal to Landolt's mechanism. And let me just maximize this window right here to maximize our real estate. And in this case, MATLAB requires that a file, or a function rather, which will be passed into its ODE solver, take in t, so time as a variable, and then the variable we are integrating, in which case, in this case rather, it's the concentration. Now, let's define a few user-friendly variable names. We have the concentration of IO3. It actually might make a lot of sense to have this right here on the side. So we have the concentration of IO3. I'll skip the indent just to keep things in the window. You know what? Let me just pull this out here. And I will... There we go. Perfect. Okay. So again, user-friendly variables, the concentration of IO3. That will be the first concentration entry in the array. We have the concentration of HSO3. This is the bisulfite, and this will be C2. And I'm just defining user-friendly variables. That's all I'm doing. We have the concentration of HiO2. This will be C3. Notice I'm just going down the list here, iodate, bisulfite, and so on and so forth, defining some user-friendly variables. You can do these in whatever order you like. This is just the order I chose. Ci will be equal to C4. Let's see, we have CH. This is the proton, essentially pH here. C5. CHIO will make this C6. We have Ci2, this is the iodine, this will be C7, and then we have CSO3, and this will be C8, and I think I got everything. We have the IO3 minus, HSO3 minus, HiO2, we have the I minus, the H plus, and notice the sulfate is missing from this list. But remember, I mentioned earlier that the sulfate is a catalyst, so it sort of is recycled in this reaction, so we don't actually include it in our mechanism. Okay, I think we've basically listed everything we need to list, and I'm just going to space things out a little bit. I like to have nice, evenly spaced definitions here. Let's do that, and... there we go. Great. So I'm going to add a comment as well. I'm going to call this user friendly variable names. Again, my spelling is questionable at best. Next, we define the rate constants, and these are in units of moles per mole per second, depending on the reaction rate. In any case, K1 is equal to 2.95 times 10 to the minus 1. K2 is equal to 2.0 times 10 to the 10. Wow, that's a very fast reaction. K3 is 1.0 times 10 to the 5. K4 is 3.0 times 10 to the 5. K5 is 3.0 times 10 to the 12. E to the 12. Again, a very fast reaction here. K6 is a nice round 2.2, if you can call that round. K7 is 1.0 times 10 to the 6. K8 is 5.0 times 10 to the 10. And K9 is 3.0 times 10 to the 3. Now, all of our rate constants are defined. We have to define our rate laws next. So what are rate laws? Rate laws define the elementary reaction mechanisms, the individual mechanisms here. And they, of course, are only a function of our reactants. and we're going to compose them into rate laws. So let's get started. Rate laws. Again, if you're not familiar with rate laws and rate constants and all this kind of stuff, go to Scott Fogler's book or your basic reaction engineering book or chemical kinetics book and brush up on this. Or, of course, if you want me to talk about it, you can leave me a comment down below, and I'll put up a nice tutorial which introduces the basics of reaction kinetics. Okay, now the rate laws will define R1. It's going to be K1 times concentration of IO3 times the concentration of HSO3. So notice how now it's quite readable, and it sort of matches the paper here. We have the rate law or rate constant K1 times the concentration of IO3 minus times the concentration of HSO3. And we're just going to keep on continuing with this. R2 will be K2 times CH IO2 times CI times CH. And at this point, what I think I'm going to do is pause the video. I'll just fill this list, and then I will come right back because there's no point in just watching me do this. Okay, our rate laws are all written up. I wrote them all the way up to reaction number 9. Next comes the actual mass balances. So, mass balances. Now, what will the mass balances look like? Just adding a little bit of space to help you view this. These will be the derivatives that I spoke of. So the first one will be dCIO3 will be equal to minus R1 plus R3 minus R4. Now, where did this come from? Well, this came from looking at these reactions right here. Notice that IO3 minus, the iodate, is consumed in this reaction, so that's minus R1. And then it is produced in this reaction, number 3, so it's plus R3. And then it is also consumed in... it is consumed in reaction 4, so it's minus R4. And what I'm going to do is go through and do this for the remaining reagents in this reaction. We'll come back shortly after the break. And we're back. Okay, you'll see I filled out the list for all of the reagents in this reaction. You'll notice that some of them have multiplied by prefactors like 2 and 3. And this is sort of the postulate of elementary reactions, where the actual rate is going to be multiplied by the order in which the compound participates. Let me clarify that a little bit. Maybe I didn't say it very clearly. Let's take a look at iodide, which is I minus, and let's take a look at its contribution in reaction 7. So reaction 7, iodide is produced with a prefactor of 2, so we have a prefactor of 2. It's that simple, and I've just done this for all of the chemicals in this system. Finally, what we need to do is to assign the mass balances to the output variables. Again, so remember how we defined some very useful variables up here. We're just going to go and define some useful, a mapping back to our output variable, which is DC right here. Let me save this. I think I misspelled the word mechanism here. Landolt mechanism. There we go. Okay, now assign output variables, and I'll go through this and I'll come back to you guys shortly. And we're back. You'll notice here I have my 8 reagents. I've just assigned them to our output variable DC, and this is it for our Landolt mechanism. Notice we're not using the variable T. That's okay. I suppose we can maybe replace it with a tilde or just leave it as it is. What else did we do wrong? HIO might not be used. Yes, that is a mistake on my part. That should be HOI. Yes, HOI. Once again, folks, having a great day here. There we go. Okay, things look good in this file. Next thing we'll do is we will open up our run file right here. Let me just pop that out. Let's see. Let me see if I can drag this somehow into the other window. Maybe not. Let's see. Doc in editor, and then let me pull out the entire editor here. There we go. Fantastic. Okay, so our Landau run file. What's the run file going to look like? The run file will contain our initial concentrations, and then we're going to call our ODE solver. So what we want to define are our initial concentrations. So define initial concentrations. And we'll just create a vector. I'll call it C0 for initial concentrations. And in here, we're going to enter the initial concentrations for all of the reagents. We have to match the same order that we supplied them in here. So it'll be iodate, bisulfite, and so on. So just keep that in mind. And the initial concentrations will come from down here. So they're listed right here. Let's get started with our iodate. That's 0.0715. And then we have our bisulfite, which is, let's see, where's our bisulfite? Did I highlight it somewhere? Aha! So what they do is they give us the pKa of the bisulfite is 7.2, and our pH is approximately 8. So what we have to do is compute what the equivalent concentration of bisulfite we will get in this system. And you know what I will do is I will leave this as an exercise for the viewer. It's pretty straightforward, but I believe in any case the number you will get will be 0.0101 for a pH of 8 and a pKa of 7.2. And next, we need to define our HiO2 concentration. This is actually 0 because it is an intermediate. It's not a reactant that's put into the system. Then it's the iodide concentration. It's 1 times 10 to the minus 6, 1 e to the minus 6. And then it's the proton concentration, the pH essentially. So remember, we said we have a pH of 8. We can compute the corresponding concentration of H plus ions, and that comes out to being 8.36 times 10 to the minus 9. Again, I'm not going through the exercise of showing where these numbers come from, in particular for the proton, for the H plus, and for the bisulfite, because the focus of this is more MATLAB and how you can solve these systems in MATLAB. But again, if you're interested in a little bit of a chemical tutorial or chemistry tutorial, let me know. I'll be happy to do that. Next up is the HiO concentration. This is 0, not a reactant. The iodine concentration, that's 0. Again, it's produced in the reaction. And finally, we have the concentration of our SO3 minus, or SO3 2 minus. This is 0.0764. Okay, so these are the starting concentrations. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 entries in here, and these represent the starting concentrations for our system. Okay, now we're going to define the time interval of our integration. So over what time span do we want to solve the differential equations? Notice how the interesting business here takes place around 5 minutes. So let's go out to, I don't know, 6, 7, or 8 minutes, something like that. Let's see, I'll define time span. I'll go T-span. Let's go 0 to 480 seconds. Okay, now we have to run our ODE solver. And in order to run our ODE solver, we need to know a little bit about the type of system we are solving. This brings us to the following interlude. I have up here a list of solvers for MATLAB, and I can tell you now the kind of solver we need is a solver for a stiff differential equation, and we'll just go ahead and use ODE 15S. But the real question is, why do we have a stiff system? And the answer to that is looking over here. A stiff differential equation is or a stiff system of differential equations is a set of equations where the derivatives of the different equations or the different variables in that system vary considerably. So the ODE solver attempts to maintain a certain degree of accuracy to the solution by taking adaptive steps. So if the derivative is very steep, it'll take small steps. If the derivative is pretty flat, it'll take very large steps. Now imagine if one equation has a very steep derivative because maybe it has a very large number in it, and another one has a very small derivative relative to this one because it has a very small number in it. What will end up happening is the solver will have to take very, very tiny steps to satisfy the accuracy requirement due to a very large derivative, and it will take forever. This is what will happen if you try to solve a system like this using the beloved and very popular ODE 45. It will just never finish. So, in this case, we have a stiff system, and by the way, most relevant chemical reactions are going to be stiff because they will have a rate-limiting step, and inherently a rate-limiting step is going to be much slower than the other steps in the system, so they will end up being stiff. They will have a much larger, much smaller k-value, for example. So we want the ODE 15S solver, define time span, and then we will say run ODE solver. I can't spell. Okay, great. Run ODE solver. What's that going to look like? Well, it outputs the time and y, so ty. That will be equal to ODE 15s. And we want to pass in a handle to our Landolt mechanism. And then we want to supply our time span and then our initial concentration. So at this point, let's dock our editor back into MATLAB, blow this window up, and then run this. Cross our fingers, of course, hope nothing bad happens, and run it. Okay, something bad did happen. Landolt. Okay, great. Just a typo, spelling mistake here. Let's run that again. And it ran without any errors. I just cleared my window, don't panic. Let's plot this and take a look at what we got. So, keep in mind, again, I keep changing my window around here. Sorry for the inconvenience, but what I want is this, because we want to compare our result to the paper, of course. What we want to do is compute the pH. So remember that the 1, 2, 3, 4, the fifth entry is our H plus concentration. This is pH over time. So what we will do is we will say pH is equal to negative log 10 of y and then the fifth column. So that should give us the pH, and then we can plot our time, which is in seconds, because those are the native units. We will divide that by 60 for minutes, and then we'll plot pH, and we'll take a look at what we got. Okay, what do we got? We actually obtained something that looks quite similar to what was obtained here in this picture, with the same little kink up here, and the same dip around 3, all the way out to 8 minutes. So it looks like we were actually spot on, and we reproduced this result perfectly, I would say, or as close to perfect as it's going to get. This is the model result. This is the actual result. So the experimental is A, calculated is B. We match the model, not the experiment. The model is not perfect, of course. And that basically summarizes this system. We could also plot the iodine concentration. Why not? Let's create a new figure, and let me drag it over here. And then let's plot T divided by 60, and then I believe it's the seventh entry, 7. And look at that. You can see that the concentration of iodine is basically 0 up until the moment where we have a drastic change in the pH. And then look at that. We form some iodine. This complexes with the starch indicator in solution and gives us that beautiful deep blue-violet color. I hope you found this tutorial useful. If you enjoyed it, please give it a thumbs up. If you loved it, please subscribe. Be sure to leave me a comment down below of what else you would like to see. I hope to do a few more videos on chemical kinetics, a few more on thermodynamics, and go wherever you folks take me. Once again, thanks for watching. It's been nice, and I'll see you in the next one. Goodbye.